Okay, this is the eighth video in the probability functions section, and in this we're looking at approximating the binomial distribution with the normal distribution. Now, this might be useful because in some circumstances it might be more convenient to do this. Traditionally, we've done this with large values of n. If we have very large samples. It's less of an issue nowadays, to be honest, because the calculators can cope with quite big numbers. In practical terms, we may be less likely to do it, but it's still a useful thing to be able to do. Now, when can we do it? When is it a reasonable thing to do? Well, if we look at this distribution here, so this is the binomial for a probability of 0.5 and a sample size of 30, and as you can see, it looks pretty symmetrical, doesn't it? So you can imagine that all these, if we actually look at the percentages of all these areas underneath here, it pretty well is more or less the same as the normal distribution. So why don't we actually just say, well, it's a normal distribution, and if we know what the mean and the variance is, then we can basically get a correspondence between this and the normal distribution. Well, we do that. We do know that. I mean, we know that the mean of the binomial is n times p, 15 in this case, which of course is right in the middle, as it would be with the normal, and the variance is n times p times q. Q being 1 minus p. So again, we know what the variance for this is because it's 30 times 0.5 times 1 minus 0.5. Which is 30 times 0.25, 7.5, I think that is. Okay, so yeah, we've got a correspondence between this and a normal distribution. If we look at the sort of when we might do this, I mean, this is if the probability goes down with the same sample size. You see, we've got something which is it's a bit skewed. Doesn't really lend itself too well to doing that that approximation. Here we've going the other way. We've actually got a relatively small probability, but a large sample size. You can see this again. This is very, very symmetrical. So these are good candidates. There's a few different rules as to when you should be able to actually apply this approximation. I think this is a reasonable one. If n times p is greater than 5 and also n times 1 minus p is greater than 5, then that would meet the criteria. Clearly, as n gets bigger and p gets closer to 0.5, then the approximation becomes better and better and better and better. So you can see these two actually satisfy those criteria. But that's not necessarily always true. I mean, this one probably does, but it wouldn't be a very good approximation. So what I'm saying is that once n gets bigger and p gets closer to 0.5, then we're going to get a much better approximation. Okay, so let's have a look, see what this means in practice. Okay, so let's just simply look at this random variable, which is binomial, large sample size, obviously 1,250, and a probability of 0.4. Well, we could probably see that it satisfies the size criteria quite well. I don't think we need to do the multiplication. And NP is 500. If we multiply, this is n and this is p, so we'll multiply the two together, we're going to get the mean of the corresponding normal distribution, and then multiply by, well, we'd have to multiply this by 0.6 then, this is 0.6, this q, and we get 300. So we could approximate this using a normal distribution with a mean of 500 and a variance of, well, just take the square root of that for convenience, of 17.32 approximately squared, this number being more or less 300. So quite simply then, this is what we got here. I've left the Z value in there, because that just comes with the diagram. But this is the sort of thing that we're looking at. We've got the mean here in the middle, and then one standard deviation is going to be, well, 17.32 away from the mean on both sides. So this is going to be how it is. And if we wanted, therefore, to use this to find, for example, the probability that X is less than 520 be here, then we can just go into our calculator, use the normal cumulative with a lower of minus 4 nines or something like that, and then the higher would be 520, and that gives us this probability 0.876. And that represents, obviously, the area to the left of the red line and underneath the curve. So there we go. So that could be convenient. All right, so that done. And if you wanted, I haven't done it here, but if you wanted, you could go in and find this corresponding probability on your calculator and match it up to this, and you'd find it would be sufficiently close. So what else we got? All right, so now we're not quite finished there. If we've got a very large value of n, I think we could just go ahead and do that approximation. But for smaller values of n, then there's a bit of a correction that we need to apply. Let's look at this. Suppose we toss a fair coin 20 times. What is the probability of getting between 9 and 11 heads inclusive? Okay, so what we want is that the probability that X is greater than, that's what this means, greater than or equal to 9 and less than or equal to 11. So we basically want these 3 bars here in the middle. Okay. Now, the center, when we think about the center of this shape, we're mapping the normal distribution on the middle of the normal distribution actually is the middle of 10. So that this first rectangle here that we're interested in here, so we're interested in it's got this arrow coming up, and this is 9, but it starts at 8.5. Okay, and similarly, the one on the right ends at 11.5. So if we map this onto the normal distribution, actually what we want is the probability this random variable falls between 8.5 and 11.5. So now that doesn't make sense in binomial terms. We're not really particularly interested in this, but when we map it onto the normal distribution, this is what we need to be comparing with, and that's the way of thinking about it. Really, is just the fact that these bars don't. We want to include all of the bar in our probability, but the bar doesn't start on an integer because the integer value is sort of represented by the center of the bar. Okay, so if you can get that, that's good. Yeah, so basically what we have to do is we have to effectively kind of stretch out from the middle. Now, if we are calculating something which is less than or equal to 11, then we're going to take our normal distribution from minus some big number to 11.5, and conversely, if we want something at the right hand end, the continuity correction becomes less significant if n is large, and if n is greater than 100, it won't make much difference. Exactly. So it's more for this sort of situation where we've got a low value of n. Now, there are tables knocking around which summarize all this. If this is this, then you add this. If this is this, you don't know. Oh, just confusing stuff. The point is, if you understand the principle as to why we're applying the correction, and yeah, if you wanted to draw a little diagram like this, and I think you could probably just think it through for yourself, then don't try remembering those tables. It's just using up unnecessary brain power. You can just think it through, and if you understand the principle. Okay, let's have another look at an example here. In an experiment, there are 250 trials, and each trial results in a success or a failure. Write down 2 of the conditions that need to make this into a binomial experiment. Simply that all the observations need to be independent and identically distributed. That's we covered that before. This does get asked over and over again. All you have to remember is IID. It is claimed that 10% of students can tell the difference between 2 brands of baked beans. In a random sample of 250 students, 40 of them were able to distinguish the difference between the 2 brands. 10% seems very low to me. When I was a student, we virtually lived on baked beans, so I would have thought it'd be much higher. But anyway, this is saying 10%. They're able to distinguish the difference. So in a sample of 250, 40 of them were able to distinguish. Using a normal approximation, test at the 1% level of significance whether or not the claim is justified. Use a one-tail test. Okay, so what we've got here is this random variable is binomial. Got an n size of 250 and a p probability of 10%, 0.1. Okay, so when we look at what this gives us in terms of mean and variance, basically a mean of 25, that's just that times that, and then we're going to multiply this by 1 minus that, 0.9, which gives us a variance of this 22.5. So if we want to use the normal distribution, then we're going to approximate it with a normal with a mean of 25 and a variance of 22.5, which square root of 22.5 is 4.743. So just for convenience, I've written it like that. Okay, so step 2, state the hypotheses and test. Well, the hypothesis, null hypothesis, is that the mean is 25. Okay, that's our baseline assumption. So because we're assuming that 10% can tell, so we would expect 25 students who can distinguish in this group of 100. And we're doing a one-tail test, so we're kind of checking. We've taken greater than. We got 40 out of 250, which is actually greater than 10%. So implies that we're interested in the upper end. It doesn't say that explicitly, but that's what we're going for. One-tail test at 1%. So if we find the p-value of the test statistic, okay, the probability that x is greater than 40, given that we've got this normal distribution. So what we want is the probability, and this is applying our continuity correction factor, that p is greater than 39.5. So therefore, that's going to give us a probability of 0.00111. Right, okay, so 0.0111 is less than the alpha value, quite a bit less than the alpha value. So therefore, we're going to reject the H0 because we're into the territory where we're saying, well, this is pretty unlikely to have happened by chance. So that's basically how that works. Okay, so hopefully that was useful. It does go on to say here, which we really addressed, comment on the acceptability of the assumptions you needed to carry out the test. Well, this is really saying whether or not we can approximate well, first of all, it's comment on this, independent and identically distributed. So I think that's extremely fair. The other one is, are we actually able to make this this approximation? And yeah, you know, we've got a very large value of n, and you know, if we to try multiplying these two together, np and nq, it's going to meet the criteria. Okay, so let's just have a look at another example. A television program called Cook Off changes 3 of its presenters. This has never happened. The program was viewed by 20% of a population of 50 million. Producers want to determine if this change has affected viewing figures. From a random sample of 100 from the population, 28 said they watched the program. Carry out a suitable hypothesis test at the 5% significance level to determine whether there is evidence to suggest viewing figures have changed. Okay, so it's just what we've got here. Just to point out, by the way, it doesn't actually say use the normal approximation here, so I've just kind of hijacked this question to illustrate the point. As with most of these normal approximations, you know, you could do it on the calculator, probably anyway. The calculators are very powerful, but you may well be asked to actually do it by solve a problem by doing the approximation. So clearly, you know you need to know how to do it. So if this random variable is the number of watches from a sample of 100, then that would be binomial with a sample size of 100 and a probability of 0.2. That's giving us a mean of 20 and a variance of 16. So we could write that like that, 16 being 4 squared. Okay, so that's that. Normal distribution would represent this this distribution, the distribution of the number of watches. So our hypothesis is that the mean is 20. So that's our kind of baseline. That's what this represents. Incidentally, this 50 million doesn't actually carry any great significance other than the fact that it means this number here is drawn from a very large population. So we're taking this as point 2 as pretty well fact. So under the null hypothesis, then yeah, we're going to expect 20% of 100 to be watching the program, and we're testing that because we've now got a sample which gives us a number which is not 20. Okay, so in other words, our test statistic. Oh, incidentally, we're doing it. We're doing a. It doesn't say otherwise. So in here we've chosen to do a two-tail test, despite the fact this is 28. I think the point with this is we don't really know whether it's increased or decreased figures, do we? So it's a little bit of an arguable point, but basically we've taken this as a two-tail test at 5%. So each tail is going to be 2.5%. Our test statistic is 28. Okay, and that's the number that said that they've watched the program. So using our correction factor, we're now actually looking at the probability that X is greater than 27.5. Okay, so that will be equal to 1 minus probability that it's less than 27.5. We're doing that because obviously our calculator does up to less than or equal to, and that's what we can calculate on the calculator, and that comes to 1 minus 0.97 to 2 decimal places. So we look that up, apply with the calculator, or 0.03. So this p-value, given that our significance level is 5%, so half of that is 2.5% or 0.025. So this 0.03 is greater than that. So basically, it's not low enough to cross the threshold into this is unlikely territory. It's not far away, but it's still actually in the sort of the middle piece of the curve. So so we are concluding therefore that it could be down to random variation, and therefore we're going to accept H naught. And H naught is that the viewing figures have remained at 20%, 0.2. Okay, so that is another example. Okay, so I think that's there will be. I'm going to do further examples videos on this topic, but at this point in time, that is the last video in this section. So, and I would just say that whilst the videos in this section are really oriented towards the UKA level, if you are interested in statistics, and I would really like to think that you are, and that my videos haven't dissuaded you in any way. But it probably, unless you're going to go into engineering or such like, it is probably the most useful part of the maths syllabus. That's my own personal opinion, because it's the sort of thing that comes up in all sorts of walks of life, in all sorts of careers. So if you are interested and you want to do some more things, either have a look at some another perspective on some of the things in these videos, or if you just wanted to look at some more advanced things, then I thoroughly recommend that you go to this YouTube channel, Z Statistics. A fellow called Justin Zeltzer has done some excellent videos. These are really, really good, and and very thorough and well presented. So I really recommend you actually have a look at these. And you might want to go into this area, distributions. This probably maps on quite well onto the onto this A-level material. Regression series, yeah, and statistical inference, hypothesis testing. They're all very, very relevant. But yeah, have a look through those, and hopefully it will make your interest and love of statistics even greater. Okay, so right, well, there's other topics, so hopefully I will see you in those.